Hello, name's Yuzi. Originally the plan was to include a slideshow in the video, but I started realizing it was getting too complex, so instead I decided to do a video. Uh, I'm quite honestly surprised that we have arrived to the end of the year. It seems like time has gone by so fast. And speaking of time, I wanted to talk and correlate everything we learned into one single video. Now, the way I would do this is in parts, obviously, but we'll basically start at the beginning of the universe when there was nothing. And the first thing I remember learning was the Big Bang, the steady state, and the nuclear fusion with the star life cycle, of course. But basically, the Big Bang and the steady state theory tried to explain how the universe was created, and the star life cycle was basically trying to explain how stars got their energy and how they grew, how they got their brightness. And basically, I know for a fact that the Big Bang theory is basically a small particle expanding like that, like massively. And the steady state theory was saying, oh yeah, everything was the same. It always has been the same. Nothing has changed. I was able to learn, that the Big Bang theory was proven true thanks to something known as cosmic microwave background radiation. Now, what this radiation proved was that the universe was expanding, since it was theorized that you would see this all around the universe. And now that we're on the topic of the Big Bang theory, when it did happen, it released a lot of space dust and space gas. Now, space dust and space gas are one of the most important things when it comes to our star formation and our planet formation, because basically you need space dust and space gas in order to get something known as the stellar nebula. Now, this nebula basically is the origin of all the stars. And with the help of gravity, the stellar nebula either becomes an average or a massive star. Now, if it becomes an average star, it becomes a red giant, which then becomes into a planetary nebula, and then a white dwarf. If it is a massive star, it becomes into a supergiant, and then a supernova, and then either it becomes a neutron star or a black hole. Now, I remember researching during this time period about the biggest black hole, which was Phoenix A. And Phoenix A was basically around 100 billion suns worth of weight. And I started to think to myself, how big could it have been as a massive star? And at the same time, I started questioning myself, how did it get that big? And this is where nuclear fusion comes into play, because nuclear fusion is basically saying I have two elements, I combine them together, but with the help of gravity, obviously. Combine them together, I get a new element and a lot of energy. That is basically it. Now, I also learned that nuclear fusion is basically in all of the star's main stages, which if you're an average star, it would be the red giant, and if you're a massive star, it would be the red supergiant. Now, I also learned that nuclear fusion is correlated to the size and the brightness of the star, meaning if you have to burn more energy, you have to use more energy to get that big, you're gonna run out of energy very quickly. And that is basically why red supergiants become into supernovas, because they run out of energy, and from what I remember, they basically collapse onto themselves and explode, and that gives us the supernova. But going back to our friends, space dust and space gas, instead of becoming a star, they become a planet. And when it does happen, the planet is obviously going to be very hot. Now, the more dust you have, it is more likely that you become a terrestrial planet instead of a gas planet. And this is where the Earth comes into play. Because basically, at the beginning of the Earth's lifespan, it was just a molten rock. It had no life. It had just CO2 in the atmosphere. And I learned that you could separate the Earth's lifespan into three different time categories, which would be eons, eras, and periods. Now, the eons are the longest time span, the eras are the second one, and periods are the last one. Now, in the eons, there's like four of them, and the most important ones are the Hadean eon, which is when there was only CO2, and this was when the floor was lava. And the second most important one would be the Proterozoic eon, which is when life started to form, and this is when something known as the Great Oxidation Effect occurred. Now, the last one is the Phanerozoic eon, and this was when complex life started forming, and this is another important one because it's basically after the Proterozoic eon, which was the Great Oxidation event. Now, if we were to take those eons and go even further, or in other words, classify them into even smaller pieces, we'd get into eras. Now, there are three eras I really wanted to talk about because they're really interesting to me, obviously. The first one is the Neo-Archean era, which was around 2.8 billion years ago. And it is believed that during this time span, the early life started forming. And early life, by that I mean single cellular organisms. Now, single cellular organisms can be classified as algae, and during this time span, basically those single celled organisms did photosynthesis in order to get their energy. And what do we know about photosynthesis? We know that they take energy from the sun, which they had, and we know that they take CO2 from the atmosphere, which we also know they had a ton of. So they started producing oxygen, and it is believed that thanks to the algae, we got the Great Oxidation event. And the next era I wanted to talk about is the Mesozoic era, which is basically the age of the reptiles and dinosaurs. Now, as a kid, I've always been fascinated by them. And the Mesozoic era goes into another topic, but I loved dinosaurs as a kid, so I really wanted to include that into this video. The next one is the Cenozoic era, which was 66 million years ago to today. And the Cenozoic era is known as the Age of Mammals. Now, if we were to go from eras to even smaller, we'd get to our periods. Now, there are three periods I really want to talk about because these are very crucial periods. The first one is the Cambrian period, which was 541 million years ago. And this was when life forms started appearing as aquatic life creatures. So, for example, trilobites are basically multicellular organisms, and they are therefore classified as complex life. Now, this goes into our time scale since this was after the Great Oxidation event when algae started creating the oxygen. And at this time too, there was also water on the surface of the earth, so it was basically a perfect place for most life to form. The next period is basically the Ordovician period, which was 485 million years ago. And this is when aquatic life actually started like developing even more. They started evolving. And finally, the last important time period would be the Devonian time period. And this was 419 million years ago. Now, at this point in time, aquatic life said, you know what, we're done being in the ocean. We're going to go on land because we're tired of being in the water. So this is when life started evolving to adapt out of the water. And since continents started forming, thanks to another important eon, which was the Archean eon, I forgot to mention it, but basically, in a nutshell, the Archean eon was when the Earth started cooling down, meaning the lava started hardening, which meant there were continents. After we got here, now that we're this far, how do we know all of this is what I was asking myself, right? I was asking myself one day, how do we know all of this? And this is where other scientists come into play. I'll obviously talk about them later. But basically, things known as continental drift and plate tectonics helped prove this. But this was only thanks to fossils and radiometric dating. Basically, as mentioned before, the Archean eon brought continents, brought plate tectonics, but there's a difference between continental drift and plate tectonics. Now, I didn't understand it at the time, I knew nothing, but basically, continental drift and plate tectonics both try to explain how continents moved around, how fossils moved around, because previously you could find two of the same fossils in different continents, and scientists of the time wanted to know why. Now, there was this scientist known as Alfred Wegener who originally came up with continental drift, and basically, continental drift was disproven because there was a lack of evidence. He just did not have enough evidence at the time to prove that this was the case. But his theory was not in vain, because his theory helped with the foundation of plate tectonics. Because plate tectonics say that there is the top layer of the earth, the lithosphere, and then the bottom of the earth, which is the asthenosphere. Now, the lithosphere are the plates we know, the continents, and the asthenosphere is basically magma under those plates. And what plate tectonics proved was that continental drift was a good idea. Sure, it was flawed, it had a lack of evidence, but plate tectonics basically fleshed that original theory out. And thanks to that, we have plate tectonics. But going back again, we needed to know how these theories came about, and that was thanks to the help of fossils. Now, basically, fossils, as a kid, I used to thought, oh, they were just cool animals. I didn't know like these could be used as time scales in order to help us organize the Earth's history. But basically, what fossils do is figure out how evolution has occurred in life. So, from our single cellular organisms to our trilobites to our alpacas, basically. And we know how to measure how old these fossils are thanks to something known as radiometric dating. Now, there is a lot to cover in radiometric dating, but basically they help us establish the age of the fossils, which only further helps us establish the Earth's lifespan, the timeline, how everything occurred. Now, I remember that the most important thing about radiometric dating is the half-life. Now, half-life is basically measuring the radiation in a fossil or in a rock in order to see how old it is. And thanks to that, we know where to place each single period, each single era, and each single eon. This is very important to understanding our Earth's history. Now, since we're here, I also wanted to talk about the other things that the Earth basically had and developed during these eons, eras, and periods. Now, the first thing, as we know, was CO2 and the Great Oxidation Effect. And when the Great Oxidation Effect occurred, something known as the atmosphere was created. And we have to thank the atmosphere that it was created, because without it, we would not be here. Now, at the same time, something known as the hydrosphere also occurred thanks to the formation of water, since from what I remember, there was also hydrogen on the Earth. And as we know, you need two hydrogen atoms and one oxygen atom, and we had that with CO2. And we also have, thanks to molten lava hardening, what we know as the geosphere. And finally, thanks to our algae, thanks to everything, we have the biosphere. And all of these interconnect with each other since you need all of them in order to have a perfect Earth. The atmosphere depends on a lot of things. For example, without our plants, which is basically the biosphere, it is unlikely that the atmosphere would even exist. Without our atmosphere, life couldn't exist. Multicellular organisms cannot exist since we need both of them to be able to exist. Now, the hydrosphere connects with the atmosphere because the atmosphere basically helps transporting the water into other places of the earth. So, in other words, condensation, precipitation, transpiration, you need all of those in order to have water on all parts of the planet. And the biosphere is also connected to the hydrosphere because plants, as we know, give transpiration, which help transport water into other places. Now, at the same time, the hydrosphere is connected to the geosphere because without the geosphere, you wouldn't have groundwater. And without the geosphere, we wouldn't have our resources. And at the same time, we wouldn't have wells in the ground. We need all of them to exist. Now, how does the atmosphere connect with the geosphere? Sadly, I don't know. Or do I? But basically, the atmosphere and the geosphere connect since wind carries basically all of the rocks, all of the sand into other places we need it to. And the biosphere obviously depends on the geosphere, and the geosphere depends on the hydrosphere. And all of these are basically connecting together into one little ball, which each single sphere connecting into each other. It's kind of cool, not gonna lie. Plate tectonics go into the geosphere, and going back to them, they contribute to earthquakes and they contribute to volcanoes because sometimes the plate tectonics collide into each other, resulting into a low mountain. And if there's a low crack under the earth because of the magma, in other words, the asthenosphere, we would have a volcano. Now, earthquakes occur because sometimes, again, they collide the plate tectonics. Sometimes they split apart. Other times they just collide like that, flat, over, split. It's quite interesting, not gonna lie. Now, there's also two different kinds of earthquakes, which I remember very clearly. Natural ones being like that, and then man-made ones which occur with damaging the geosphere, which eventually results into an earthquake. Now, I'll continue going on to the geosphere because it's still a lot of things we have to go through in the geosphere. But in the geosphere, we have soil, and soil is technically, to me, part of the geosphere, but it is also part of the biosphere. Soil is basically connected to the geosphere and the biosphere since soil is a living thing. It's not like sand. Sand is not living. Soil is, not sand. And that's because there's life within the soil. Soil basically helps with the plants, and in the soil there's these things called minerals, and we depend on minerals too. Keep in mind, we depend on the geosphere to give us those minerals. The soil also depends on the minerals because it basically gives them nutrients in order to become richer, better in everything. I remember doing a project earlier in the year with soil. Originally, that was going to be my science fair, but it never worked out. But basically, in the soil, I learned that it's important to know what kind of soil you're working with, because if the soil is too soft, it might let water through, meaning things such as floods are more likely to occur. If it's too hard, basically it's not good for planting since the soil is way too hard. Soil also contributes to our buildings. If the soil is too soft, the building might collapse. As we know at MIT, it took forever to actually build the second building. But now they started, obviously. It's too late. I thought I was gonna enjoy it in 7th grade, but I guess not. But all of these are connected, Everything is connected. Life, everything. Um, but continuing on with the geosphere, humans have impacted it with the extraction of resources. And we know that our resources are very limited. We don't have a ton of them. Although we do have a ton of them, it's not enough for future generations. Or, in other words, there is not enough resources to support the now and then the future. We're using too much too quickly. And this is when, sorry, I had to get comfortable. And this is when we go into the present time, like a few months ago, when we learned about sustainability and economic growth and how both of them have their differences and whatnot. Economic growth states that our economy grows bigger, and sustainability means sustaining our resources to make sure that we have enough for now and the future generations. Now, after the debate we did, I came to the conclusion that you basically need kind of both of them because economic growth helps boost a little bit sustainability because you develop and invest more into sustainable approaches to our environment. And sustainability depends on economic growth since sustainability is kind of expensive from what I remember researching. Solar panels, windmills, dams are expensive. It's expensive. How are you going to pay for that without economic growth? But obviously, in the debate, as you know, I was basically on the sustainability side. Now, I came to the conclusion that I could have prepared better, obviously, but I did enough. We did enough in my team, obviously. We all did enough. We all contributed our parts. Hector helped with the research. Manuel helped with speaking. I'm not really good of a speaker when it comes to debates. Um, I helped with the research, obviously. Some of the questions, too, we gave to the other team. But yeah, that's basically it. I said I was going to talk about the scientists, and that is exactly what I'm going to do. It's late at night, but I wanted to talk about the scientists, so I'm going to make this really quick. The first scientist is Claudius Ptolemy, and he basically came up with this model known as the geocentric model. And this basically put the Earth at the center because, from their perspective, everything else rotated around the Earth. Obviously, this was the best theory they could come up with at the time on how everything in the solar system worked. But then Nicholas Copernicus basically came up with the heliocentric model, which basically placed the sun at the middle because it would rotate around all the planets. Now, this was seen as not true. It was argued by a lot of people, but eventually it was proven to be true, but later in the future. There was more information added onto it thanks to Johannes Kepler. And what Kepler did was explain how all the planets moved around, and in other words, give us the foundation to astronomy. And this was thanks to the law of planetary motion. And this, as mentioned before, continued describing the heliocentric model. Then the heliocentric model was proven thanks to Galileo Galilei. But basically, Galileo continued developing the telescope, which he eventually saw phases on Venus. Now, the only way you can see phases on Venus is thanks to what? If the sun was in the middle of the entire solar system. Now, Johannes Kepler, with his laws of planetary motion, basically influenced Isaac Newton with his laws. And Newton basically came up with the laws of motion. These laws of motion explained how objects interacted with each other and their motion, obviously. Thanks to Isaac Newton, we know about elliptical orbits, which basically means that the orbits around the sun aren't in a circle, but rather in more oval shape. And he, with his discoveries and laws of motion, influenced modern science, what we know of today. But now that I've basically talked about everything I can think of for this video, I want to thank you, Miss Coleman, for teaching me a lot this year. This video was kind of bad, I guess. But I want to thank you so much for all the teachings you gave us and all the yap sessions we had. They were really eye opening, and yeah, I hope to see you next year, Miss.